Here we have a graph of the function f of x equals x squared plus 1. As you can see, for positive x, the function is actually increasing. We are interested in the area under the graph and above the positive x-axis. This area is confined between the vertical line x equals 0 and the vertical line x equals 2. We can approximate that area by these four rectangles. These four rectangles will give us an overestimate of the area. Each of these rectangles has the same width, delta x. Now, because we have four rectangles, we need to divide the length of the interval by 4. The length of the interval is 2. 2 divided by 4 is a half. Because the function is increasing, the height of each rectangle is got by getting the value of the function at the bottom right corner of each rectangle. So if we want to get the area of this first rectangle, we need to get its height, and that's going to be the value of the function at the bottom right corner, which is 0.5, multiplied by the width delta x. Well, delta x is a half. To get the area of the second rectangle, we get the value of the function at the bottom right corner, that is at the value of f at 1, and multiply the height by the width. The width is also a half, and so on. So the area of the next rectangle is f of 1.5 times a half, and the area of the last rectangle is f of 2 times a half. Okay, let's get f of 0.5. Well, that's 0.5 squared plus 1. That's a quarter plus 1, or 1.25. We can actually factorize out a half. F of 1 is 1 squared plus 1, which is 2. F of 1.5, 1.5 squared is 2.25, plus 1 is 3.25. F of 2, 2 squared is 4, plus 1 is 5. And we can factorize a half out of it. That makes it easier, actually. The widths of the rectangles don't have to be equal, but it's easier when they are. We could actually write this upper sum using the sigma notation. So you see, we have to multiply f of a value times the width delta x. Now, what can be a little bit tricky is finding out the form that this thing has. Now, we don't have to worry too much about this. I'm only showing you this notation so I can explain where the notation for the definite integral comes from. But anyway, I'll still go through it. It's easy to see by substituting here, actually. We start off with I equals 1, plug 1 in for I, we get f of 1 over 2. Well, that's f of a half, and that's multiplied by delta x, which is a half. Then we plug 2 in for I. Well, we get f of 2 over 2, that's f of 1, times delta x, which is a half. Then we plug 3 in, we get f of 3 over 2. Well, that's f of 1.5 times a half. Finally, we plug 4 in, f of 4 over 2. Well, that's just f of 2, and that's multiplied by delta x, which is a half. So this makes sense. This number on top here is the number of rectangles that we're using. We could imagine repeating this procedure for more and more rectangles. So we could take 5, 6, 10, 20, 50, 100, as many rectangles as we like. We just have a bigger calculation. As the number of rectangles increases, the width of each rectangle, delta x, will obviously decrease. Okay, let's see this in action. Let's suppose that n is equal to 1. So here is our overestimate for the area under the curve between 0 and 2. Note, by the way, that the scale on the x-axis is different from the scale on the y-axis. That's just to make it easier to see what's going on. Well, in this case, delta x is just equal to 2. Here we have it. We just divide the width of the interval, which is 2, by the number of rectangles n. So n is 1 here. So we get 2 divided by 1, which is 2. The height is f of 2. Well, you can see f of 2 is actually 5. 2 squared plus 1. So the area is 10. So we just have one term in this sum. We just have one rectangle. Now let's increase n. There's n equals 2. Now we have a better estimate for the area. The area of the rectangle, the upper sum is 7. This is n equal to 3. Here's n equal to 4, as we saw already. There's n equals 5. n equal 7 and so on, you can see that the area of the rectangles is approaching the area under the curve as n increases. You can see also that delta x is decreasing. Here delta x is 2 over 82, now it's 2 over 83, and so on. So delta x gets smaller and smaller as n gets larger and larger. The upper sum is actually approaching a limit. That limit is actually the area under the curve from 0 to 2. Now of course we can keep going forever like this and we'll never reach the answer. So let's see how we can calculate this area exactly. To do that, we first of all need to calculate this sum for a general n. We just calculated it for n equal to 4, just 4 rectangles. So we need to consider what this sum will look like for a general n. And when we've done that, we will then let n go to infinity. So we will take the limit as n tends towards infinity of this quantity here, just like we saw in the simulation. And if we can calculate this limit, we will have the answer. Now, in many cases we can't, but in this case we can actually calculate this limit. As a matter of fact, for a general n here, we won't have I divided by 2. It won't actually work out quite as simple as that. We'll need to work out what this general term is, and we also need delta x in terms of n. Anyway, let's look at the general case. So, okay, we have n rectangles. What is delta x? Well, delta x is the width of the interval, which is 2, divided by the number of rectangles, which is n. So in the example we just saw, n was 4, so 2 divided by 4 is a half. But in general, delta x will be 2 over n. And it's clear that as n gets bigger and bigger, 2 over n is going to get smaller and smaller. As n tends towards infinity, 2 over n will go to 0, so delta x will go to 0. So in general, what is the coordinates? What is the x value of this point? Well, the y value is obviously 0. What is the width of this rectangle? Well, the width is equal to delta x. The width is 2 over n. So this point in general will be 2 over n. This point here is 0. 0 plus 2 over n gives us 2 over n. In the example we saw, 2 over n was 0.5. What's the value of this point here? Well, we just add 2 over n onto 2 over n. That will give us 4 over n. To get this point here, we add 2 over n onto 4 over n to get 6 over n. And so on. We keep going. Okay, so you've got to imagine a general case where we have n rectangles. N can be any number, not necessarily 4. Okay, so this is what the area will look like. To get the area of the first rectangle, we have to get the value of the function at 2 over n, the bottom right corner. So that'll give us this distance here. That's f of 2 over n. And we need to multiply the height by the width. As we saw before, the width is 2 over n. Height by width gives us the area of the rectangle. And we do the same for the next rectangle. We get the height, which is f of 4 over n. And we multiply that by the width, which is 2 over n. Delta x is the width. It's the same for every rectangle. Now, how far does this thing go? Well, the last rectangle will be given by what? Well, this value is 2. So the height of the last rectangle is f of 2. And we take that height and multiply by the width, which is 2 over n. That's how we get the area of the last rectangle. Notice that the highlighted numbers follow an arithmetic sequence. The first term, a, is 2, and the common difference is 2, because 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8, and so on. Let's see what the general term is. Now, I won't call it the nth term, because I don't want to confuse the n in the formula for the general term of an arithmetic sequence with the n that's used here, which refers to the number of rectangles. So instead of tn, I'll just say ti. So this is the ith term that we saw, we saw the letter I being used already to denote the number of the rectangle. So A is 2 and D is 2. So we're going to get 2 plus 2i minus 2. That's 2i. So now our area series will look like this. And the term in here is 2i. And we can easily check this. If we just plug 1 in for I, we get f of 2 times 1 over n. Well, that's f times 2 over n times 2 over n. If we plug 2 in for I, the next value of I is 2. 2 2s are 4. We get f of 4 over n times 2 over n, and so on. You see, we will indeed generate this series. Now, to calculate f of 2i over n, we just go up here, of course. F of 2i will be 2i all squared plus 1. Actually, we're plugging 2i over n in, so we'll have 2i over n squared plus 1. So we simplify this down a bit. We have to multiply in by 2 over n. Now let's see what this thing means. Well, we plug in I equals 1. So we get 8 times 1 squared over n cubed plus 2 over n. That's the first term. To get the second term, we plug in I equals 2. So 2 goes in for I. We have 8 times 2 squared over n cubed plus 2 over n. To get the third term, we would plug in I equals 3, and so on. We would keep going until I gets as far as n. So if we plugged n in for I, we would get 8n squared over n cubed, and then the rest of it is 2 over n. So we have n terms. So this is one, the first term, this is the second, this is the nth term. But notice that we can factorize 8 over n cubed out of this. Well, at least out of these terms here, the first part of each term. And we're left with the sum of the squares of the first n natural numbers. Now we also have these 2 over n's to consider. So how many times do they appear? Well, they appear n times because there are n terms. This is the first, this is the second, this is the nth term. So we have n of these, n 2 over n's. N times 2 over n. Well, that's just 2. Now, if you've done sequences and series, you might know that a formula for the sum of the squares of the first n natural numbers was derived. So you can just look this up. The sum of the squares of the first n natural numbers is actually given by n times n plus 1 times 2n plus 1 over 6. So we need to know the nth one, and just whatever it is, if n is 7, we just plug 7 into this, and we have the sum of the squares of the first 7 natural numbers. Okay, if we multiply this out, we get 2n cubed plus 3n squared plus n. Next, I've multiplied the 8n cubed into the top. 8n cubed by 2n cubed is 16. 8 over n cubed by 3n squared is 24 over n. 8 over n cubed by 1n is 8 over n squared, and the whole lot is divided by 6. Now we saw that for n equals 4, the upper sum was given by 5.75. So, you know, you could check this by plugging 4 in for n, and you should get 5.75. I won't bother doing that. So remember, this is the way the upper sum appeared for this particular problem, and it's given by this here. Now we want to take the limit as n tends towards infinity, as the number of rectangles gets larger and larger. Obviously delta x will get smaller and smaller. So what's going to happen to this as n gets larger and larger? Well, as n gets larger and larger, both of these fractions will go to 0. So in the limit as n tends towards infinity, the upper sum is approaching this number here. Of course it never reaches this number, but this is the number that it is approaching. We can make this thing as close as we like to this thing here by making n as large as we like, as large as possible, as we need to. So the upper sum is approaching this quantity here, and this is actually the area under the curve. Let's see that again. If we keep on increasing the number of rectangles, you can see that we're approaching a limit. Here with n equal to 1000, the upper sum is 4.67. we're actually approaching 4.6 recurring, or 4 2/3, when we take the limit of the upper sum as n tends towards infinity. Now it can be proven that this sum is equal to the definite integral of f of x dx from 0 to 2. We will give some justification for this in a later video. This integral is called a definite integral because we know the bounds of the region that we're getting the area. When we don't know what the bounds are, in particular when we don't know what the left bound is, we have what's called an indefinite integral. I'll just explain a bit about the notation. When we take this limit as n tends towards infinity, delta x, as we know, goes to 0. So we replace delta x with dx, and we replace what's inside the brackets here with x. We also replace the sigma symbol with this elongated S-shaped symbol. We can think of S for the sum of what comes after. So we're actually summing the areas of infinitely thin rectangles whose height is f of x and whose width is dx. Now, as an aside, we could have also have considered lower estimates for the area under the curve between 0 and 2. So this is these rectangles, the area of these rectangles give what is called a lower sum. So in this case n equals 3, and the area is less than 4 2/3 obviously. But the thing is, the area under the curve between 0 and 2, or the definite integral between 0 and 2 f of x dx, lies between the lower sum and the upper sum. So I can increase this, of course, and you can see now the lower sum is approaching from below the area under the curve. Now the formula for getting the lower sum is slightly different than the formula for getting the upper sum. You see that we have 2y minus 2 over n instead of 2y over n. That's because we're getting the value of the function at the bottom left corner of each rectangle now. I won't go into this. You just need to know that the area is going to be less than the definite integral between 0 and 2 of the function, which is fairly obvious. Let's see the lower sum and upper sum together. So here is the picture for n equals 1. The lower sum is here in blue. So I'll just keep on increasing n, and you can see what's happening. The area under the curve that we're looking for is squeezed between the lower sum and the upper sum.